Section 10.4, Absolute and Conditional Convergence. In the last section, we were looking at series with only positive terms, but what if sometimes we have terms that are less than or equal to 0? How can we check for the convergence or divergence in those situations? So first, to answer that, let's begin with some definitions. And that is, we say that the series, a general series, summation a sub n, converges absolutely if the sum of the absolute value of the a sub n converges. So notice this is a descriptor about the original series. If this original series has the property that when you take absolute values that this new series converges, we call the original series absolutely convergent. On the other hand, if the original series sum of a sub n converges, but the new series, the sum of the absolute value of the a sub n diverges, then we say the original series sum of the a sub n converges conditionally. So we have the concept of absolute convergence and this concept of conditional convergence. Let's look at an example. So suppose we have the sum from n equals 1 to infinity of minus 1 to the n minus 1 over n squared, and we want to show that this converges absolutely. So here's how. If we acted like we didn't know this and we just wanted to check whether this converges absolutely or not, we would just take the sum of the absolute value of the a sub n's, and the sum of the absolute values, you can see what this does is it just eradicates this alternating, this minus 1 to a power here and just turns this into a 1. This stays the same. And if you stare at this new series, it's familiar to us. It's a p series with p equals 2, which is greater than 1. Therefore, it converges. Since this series converges, we just showed that the sum of the absolute value of the a sub n converges. And so the original series is absolutely convergent, or we say it converges absolutely. Why do we care so much about absolute convergence? Is because absolute convergence implies regular convergence. So absolute convergence implies regular convergence. If the sum of the absolute value of the a sub n converges, then the a sub n converges also. You can see the text for the proof, but the idea is that it's basically a comparison. If this is larger than this and this converges, then this has to converge also. There's some details in the argument that you need to look at to make sure the inequalities work, but that's the gist of the argument. So again, the key idea is that if the sum of the absolute value of the a sub n converges, then the sum of the a sub n converges. Be very, very careful. The converse is not true. Just because this converges, when you take absolute values, maybe this converges and maybe it doesn't. And the reason you're not sure is because when you take absolute values, this got bigger when you go this way. When you take absolute values, these got bigger. And so maybe it gets so big that it destroys the convergence and leads to divergence. Let's look at an example. So since the series in example 1 converged absolutely, we know by theorem 1 that the original series converges. So that's the idea. If you want to know about the convergence of this, a very quick and easy way to determine the convergence of a series is just to check if it, of a series that might have negative terms, doesn't have always positive terms, is just check the sum of the absolute value of the a sub n's. If that new series converges, then you're guaranteed that the original series converges also. So what happens though if we don't get so fortunate like in this situation? What if the sum of the a sub n doesn't converge absolutely, but we sometimes have, maybe always have negative terms? How do we test for convergence or divergence in that situation? Because we really got off really lightly in this last example because we were so fortunate that we get absolute convergence. We're not always going to get that, so we can't rely on it. So what do we do then? And this leads us to the so-called alternating series test. And it says, assume that your b sub n is a positive sequence that's decreasing and converges to 0. So this is decreasing, and the limit goes to 0. And it says, then the following alternating series converges. Notice that this is not a claim about general series with sometimes positive and negative terms. It has a very important look to it, and it just looks like the sum from n equals 1 to infinity of this sign alternating term, minus 1 to the n minus 1, just this term just flip-flops between 1 and minus 1, 1 and minus 1, 1 and minus 1. So that's where the alternating comes from, times the b sub n's. So the b sub n's themselves must be positive, so it's not destroying the alternating nature of this series. They must be decreasing, and they have to decrease all the way to 0. If that's true, then we have convergence of this alternating series. If these three conditions are true, then the alternating series converges. This is something about an error bound that we don't really need to concern ourselves with. This is really what we want right here. So let's look at an example. Let's show that the alternating series, summation from n equals 1 to infinity, of minus 1 to the n minus 1 over n converges conditionally. So to show that it converges conditionally, why don't we first show that it does not converge absolutely, just to give us some practice with that concept. But that's what conditional convergence means. It means it converges, but it doesn't converge absolutely. So we'll show that the series doesn't converge absolutely because we'll look at the sum of the absolute value of these. But then that just gets rid of this alternating sign term and makes it a 1 over n, sum of 1 over n. But this is a harmonic series, and we already argued that this diverges. So we know that the sum of the absolute a sub n's diverges, so this is not absolutely convergent. But let's show affirmatively that it does converge conditionally, because it might just diverge in every way. You have to be careful. So does it converge conditionally? Well, let's look at the sequence, or the series, that we have. And let's just write this, and why don't we just check this as, let's rewrite this so we can spot what the b sub n's are. Here I'm just peeling off because the form of the alternating series test makes us write minus 1 to the n minus 1 times our b sub n. So I'm just writing this to emphasize this whole thing as our b sub n. Our b sub n is 1 over n, so let's check all of the hypotheses. Is b sub n positive? Yes. Is b sub n decreasing? Yes. Does b sub n limit to 0? Yes. Since all three of these hold, and you do need to show these in all of your problems, since all three of these hold, by the alternating series test, we do get convergence. Notice that if any of the criteria or the hypotheses of the theorem fail, it doesn't necessarily mean that you have divergence. You just can't conclude anything. The theorem says that if these conditions are fulfilled, then you're guaranteed to get convergence. Okay? So note that this series, once again, it is related to something that we've studied before. When you took the absolute value, you got the harmonic series. Notice that this is just a harmonic series that alternates signs with a +1 and a -1. So this is called the alternating harmonic series. Notice it looks like the harmonic series, it's just flip-flopping signs here. So very key thing here that you need to definitely have in your repertoire is that what the harmonic series looks like, what its name is, and knowing that it diverges. But on the other hand, as we just showed, the alternating harmonic series actually converges. So this is a classic example of a conditionally, but not absolutely, convergent series. Let's look at another example. Let's determine whether the sum from n equals 2 to infinity of -1 to the n over n ln of n converges, or conditionally or absolutely. Well, let's first check absolute convergence. You should always check this first, because if you get this, you're done. You have absolute convergence, which implies regular convergence. So we need to take the sum from n equals 2 to infinity of the absolute value of the a sub n's. That's just, those absolute values are just going to take care of this -1 to an n and leave everything else alone, because for n greater than or equal to 2, everything here is positive. And now we have to determine the convergence or divergence of this. And so when we stare at this, you might think, how do I tackle this? Do I use a direct comparison? Do I use a limit comparison? Do I use an integral test? I would suggest using an integral test. And so if we do use an integral test, but we need to be prepared to use any of our tests, because when we take these absolute values, we may have to work for it a little bit. It might not just fall in our lap here where we know exactly what the series is doing like it did in the other examples. So if we use an integral test, we've done this a few times, so I'll go through the details quickly. It tells us what our f of n is, and therefore what our f of x is. We'll check the hypotheses. F is indeed positive, decreasing, and continuous for x greater than or equal to 2. So I just need to look at this improper integral, which is the limit of this proper integral. We'll do a u substitution, including limits, to get this new integral. We'll anti-differentiate and evaluate between limits. And then we'll take the limit as r goes to infinity. We get this ln of the absolute value of ln of r, but we don't panic. As r goes to infinity, the ln of r goes to infinity, so this is going to infinity. Then we're taking the log of something that's going to infinity. So this term's going to infinity, and this is just a finite number. So this overall limit is infinity, and since the improper integral went to infinity, the improper integral diverges, and therefore by the integral test, the associated infinite series diverges also. So after that work, we just showed that this series, the original series, does not converge absolutely. So what about conditional convergence? We'll take the original series as it stands. This looks like an alternating series to me. So I will peel off the b sub n's. Be careful, a common error is people take this to be the b sub n. But remember, the b sub n should be written as a product times the alternating series here, this minus 1 to a power. And so the b sub n's are actually 1 over n ln of n. So let's just, thinking about the alternating series test, let's check. Are the b sub n's positive? Yes, for n greater than or equal to 2. Are the b sub n's decreasing? Yes, because I have a 1 over something that's positive and increasing. So that means the quotient is decreasing. And the b sub n's are also going to 0. Again, because the denominator is growing ever bigger, and it's a 1 over that, so this is going to 0. So by the alternating series test, this series converges. And so our grand conclusion is that our original series converges conditionally, but not absolutely. Finally, this is not a convergence test, but it is something that's very important and going to become more important as we go through chapter 10, and that is finding error bounds for various series. And the reason error bounds are important is because oftentimes in real life, when you're adding up infinitely many things, you may be able to do that in theory, but in practice, you have to cut that sum off after some finite number of terms. And one thing that we want to be able to do is, if we have an infinite series and we truncate it after, say, capital N terms, we'd like to know what that nth partial sum, how far it could be from the true sum. So we call those error bounds. How far away would an nth partial sum be from the true sum of a known to be convergent infinite series? So an answer for that, at least in the context of alternating series, is the following. So suppose you have an alternating series, and let's suppose it converges, and let's call it sum s. Whether we know it or not, we know we can easily, just like we did in this last example, we can rather straightforwardly deduce when this infinite series converges. We may not know the value that it converges to. That's a completely different story. But we know that this infinite series converges. Then what the error bound says is, if you have a convergent alternating series, and you call it sum s, then if you look at the difference between the true infinite sum and the nth partial sum, that the absolute value of the difference, so the absolute error there between those, is bounded above by b sub n plus 1. So it's the next term in your infinite series, or the absolute value of the next term in your infinite series. So if you disregard the plus or minus sign. And so as a practical example, let's look at this one. Let's take the same series we've been using earlier. Let's take the sum from n equals 1 to infinity of minus 1 to the n minus 1 over n squared. We already showed that this converges absolutely in example 1. The question now is not about convergence or divergence, but hey, we know it converges. But if we were to take the 10th partial sum and we were going to use that to approximate the true sum, how far off could we be? So what's the maximum error that you could have there? Well, from our error bound, we first just need to think of, if we take the nth partial sum, so here this is actually a 10 here, so I'll fix that. Then we have the sum from n equals 1 to 10 of minus 1 to the n minus 1 over n squared. And this is what that 10th partial sum looks like. Notice, just like we did before, if we peel off, the b sub n is actually 1 over n squared. And so using the error bound, it just says that the difference, the absolute value of the difference between s and s10 is less than or equal to b11. b11 in this case would be 1 over 11 squared, which is 1 over 121, which is approximately 0.008. And so that tells us that if we just take the first 10 terms in the series and sum those up, that will be within 0.008 of the true sum.